Hi, I'm Amir Hossein Mirza Bozorg, and in this video I want to talk about element deletion in Abaqus based on CDM. CDM is the abbreviation of Continuum Damage Mechanics. This is the table of content. I will talk about status in field output request, SDEG in field output request, DMI CRT in field output request, choosing appropriate step, static general step settings for damage analysis, mesh design for damage analysis, element specifications in damage analysis, comparison of the effects of mesh module settings on the result of tensile test simulation, element deletion settings, force displacement curve of tensile test, element deletion versus no element deletion, and finally Mises stress equivalent plastic strain curve for deleted elements. In the Abaqus, equivalent plastic strain variable is PEEQ. In continuum damage mechanics, damage propagation in the material is modeled by deletion of completely damaged elements. For simulating damage propagation, at first you must define damage initiation and damage propagation or damage evolution criteria in property module. In addition to these settings, there are several options in a step and mesh module to have more control on the damage propagation analysis. In this video, these options and the effect of each of them on the simulation results are explained in detail. Actually, for having element deletion in the simulation results, you must define damage initiation and damage propagation criteria in the property module. Then there are the other settings in the step and mesh modules. In this video, I will talk about these settings. They have direct effect on the simulation results and the element deletion. I want to talk about status in field output request. This is the field output request, and in this section I have activated a status. By activating this option, if the element deletion is activated in the mesh module, the completely damaged elements will be removed from the analysis. The other parameter is SDEG in the field output request. SDEG is the damage parameter. Its contour shows the damaged areas. In the damaged areas, its value is greater than 0. Its value is always between 0 and the maximum value of damage parameter that is specified in the mesh module. In the next slides, I will talk about how to change the maximum value of damage parameter, and its default value is equal to 1. The other variable is DMI CRT. In the regions that the damage mechanism is initiated, the value of DMI CRT is equal to 1. At the start of the analysis, its value is equal to 0 in every point. As the loads are increased, its value increases gradually from 0 to 1. In the regions that its value is equal to 1, the value of SDEG will start to increase from 0. Actually, the DMI CRT variable corresponds to damage initiation, and SDEG variable corresponds to damage propagation. So, during the simulation, when the load is increased, at first DMI CRT starts from 0 to 1. Then the damage is initiated in the regions that the DMI CRT value is equal to 1. So the damage mechanism is activated, and if the load continues to increase, so the SDEG parameter starts from 0 to 1. I want to talk about choosing appropriate step for damage analysis based on CDM. As you know, we have two structural solvers in Abaqus. Abaqus Standard and Abaqus Explicit. If you want to perform damage analysis by using Abaqus Standard, you can use a static general step or dynamic implicit step. And if you want to use Abaqus Explicit solver, you can use dynamic explicit step. If you use one of these steps, as the introduction of damage to a model makes the analysis highly nonlinear, in complex damage problems, convergence issues may arise. It's because of the use of implicit algorithm by these steps. And if you use dynamic explicit step, introduction of damage to the model and increase of degree of nonlinearity makes no problem for Abaqus Explicit solver because it uses explicit algorithm. Even the most complex damage problems can be solved by using this step. I want to talk about static general step settings for damage analysis. If you are going to perform a damage analysis by using a static general step, it's better to activate automatic stabilization. By activating automatic stabilization, virtual viscous damping forces are introduced to the model. This value helps the highly nonlinear problems to converge faster. So the possibility of getting convergence errors like too many attempts and minimum time increment will decrease. And in the incrementation tab, you must set these values according to these equations. T is the value of time period, and here I have used these equations for setting these values. For example, here the value of time period is equal to 1 and initial time increment size must be less than 1% of time period. So I have set it to 0.001 and I have done this for maximum time increment size 2. There are several settings in General Solution Controls Editor. For performing a damage analysis, it's better to activate discontinuous analysis. So the value of these parameters increases and it helps the solver. And it's better to increase the maximum number of cutbacks in each increment. Its default value is 5 and it's better to increase it to 10 or 15. Now I want to show you these settings in the Abaqus. In the step module, for field output request, failure fracture section, I have activated SDEG and DMI CRT. And in this section, I have activated status. I want to show you the general solution controls settings. I must activate discontinuous analysis and I must increase the value of IA. Here I want to talk about mesh design for damage analysis. This is a 2D model of tensile test and I want to talk about this model. Small elements must be used in the regions where the damage initiates and propagates. I'm talking about this region. In these regions, the aspect ratio of elements must be near to 1 because the aspect ratio of an element has an important effect on its damage behavior. For 2D elements, the aspect ratio is the ratio of largest length to the smallest length of the element. If you are forced to decrease the number of elements in the damage initiation regions similar to the far field regions, you are allowed to increase the aspect ratio of elements up to 5. Actually, the aspect ratio of an element has a direct effect on the damage propagation. And if the value of aspect ratio increases, the accuracy of the damage propagation simulation will decrease. Here I want to talk about element type settings. In element controls, we have two settings, element deletion and max degradation. About element deletion, by default, if an element is damaged completely, it will be removed from the model. But it can be changed so the fully damaged elements will remain in the model. If I set element deletion to no, even the fully damaged elements will not be removed from the simulation. About max degradation, by default maximum value for damage parameter is 1. But you can decrease it and use smaller values between 0 and 1. This will affect the force displacement curve and the loading capacity will decrease faster. I can set it to specify and enter a value between 0 and 1. For example, 0.9 or 0.6. For comparing the effects of mesh module settings on the result of tensile test simulation, 4 models have been created. These models only differ in the settings of mesh and step modules. All of the other settings, including settings of property module, are the same. The differences are presented in a table. I have created 4 models: Model 1, Model 3, Model 4, and Model 5. We do not have Model 2. And I have performed 4 simulations with different settings. In Model 1, status is activated, element deletion is set to default, and max degradation is set to default. In Model 3, status is activated, element deletion is set to yes, and max degradation is set to 0.9. In Model 4, the status is not activated, element deletion is set to no, and max degradation is set to default. In Model 5, status is activated, element deletion is set to yes, and max degradation is set to 0.6. Here, you can see the force displacement curve of 4 simulations. The red curve is related to Model 1, the blue curve is related to Model 3, the purple curve is related to Model 4, and the green curve is related to Model 5. In the next slide, I have magnified this region. Here, you can see that in Model 5 result, the force displacement curve is dropped faster and even in results of Model 3. Because in Model 5, the max degradation value is set to 0.6 and in Model 3, it is set to 0.9. Job 1 corresponds to Model 1 and Job 4 corresponds to Model 4. In Model 1, the element deletion is set to default and the status is activated. And in Model 4, a status is not activated and element deletion is set to no. So you can see that here no element is removed. But here the fully damaged elements are removed and the specimen is divided into 2 parts. Here we have plotted the Mises stress versus PEEQ for one of the removed elements. This element is removed in all of 4 simulations and you can see 4 curves. Blue curve corresponds to Model 1, orange curve corresponds to Model 3, pink curve corresponds to Model 4, and brown curve corresponds to Model 5. Here you can see that the Mises stress value is dropped faster in the result of model 5 because we have set the max degradation value to 0.6, and in this point the max degradation value is reached to 0.6 for the integration point of this element, and here it is reached to 0.9, and here it is reached to 1. You can see the effect of max degradation value on the results. And I want to show you all of these curves in the visualization module of Abaqus CAE. We have 4 jobs. Job 1, job 3, job 4, and job 5. And I want to show you the force displacement curves. I create XY data from the history outputs. They are here. Now I combine them. I choose combine operator. I change 1, 2, 3. Now I plot them. The elements are removed, but here they are not removed. At first, these 2 elements will remove. Their numbers are elements 14 and 15. I select element 14. Now we have them here, and I combine them. This is the elastic region. In the elastic region, PEQ is always equal to 0. This is the plastic region, and this is the damage region. Here we are tracking the stress strain curve of 14th element. You can contact me by using Telegram or WhatsApp, and you can send email to me. We can have one-on-one tutoring on the AnyDesk WhatsApp, and I can make special videos to your order. We can perform high-quality simulations for your thesis, exercises, and industrial projects. Thank you so much for watching this video. Goodbye.